available for remote sensing because we have a lot of absorption due to the atmosphere properties at the Earth's surface. But this range can be used, for example, to study other planets with not the same composition. And also we use, this is a French document, so you can see micro-ondes, this is microwave. So this is the hyper frequencies, what we call the radar, or also synthetic aperture radar data. So an example at a very large scale using meteorological satellites. This is a perception of the Earth by Meteosat. This is Meteosat second generation, the last generation of meteorological satellites of Europe. This is not exactly the European Space Agency, but it's another European agency dealing with these satellites. And you can recognize even its European satellites, but you can only have a very small view on Europe because Europe is small and Europe is to the north. So it's not easy to discriminate. You can only see the shape of Western Europe with Brittany here in France. And you can see mainly the Africa continent and the Middle East here and the Atlantic Ocean. So this is a view in the visible range. So you can mainly see vegetated areas in more or less dark gray. The mineral areas, especially the Sahara here, in light gray. Water is in dark gray or in black, and the clouds, or some clouds, are white or very light gray. So this is the Earth in the visible. At the same time, you have an acquisition in another range, the so-called water vapor range. That is to say, you have here the wavelength, about 6 or 7 micrometer. So it's totally impossible to identify any boundary between the continent and the sea, because all the features here are due to the water content in the atmosphere. So you have some clouds, but also the humidity and moisture is particularly dense in the intertropical area. And another range is a thermal infrared range, about 10 to 12 micrometer. And in this case, you can recognize clouds, the sea, and some parts of the continent. And particularly, you see here, you have in black color some areas corresponding more or less to vegetation, that is to say, relatively cold areas, whereas the mineral areas are of high temperature. So it's just a comparison, you see, and the perception deeply depends on the spectral range used, and it is necessary to know what are the properties of every range. Another example, in this case, sorry, it's an American example from GOES 16. It is a satellite from the National Oceanographic and Atmospheric Administration, the NOAA, in USA. And it is quite the same than previously illustrated, but you have the boundary of the different states of the United States. This is not for the results of the poll, but this is for location of the different places. For example, here, Florida is under clouds, when Texas is cloud-free. In the visible, here it is another view in the water vapor range. So it's not possible to define the continent, but you can see the moisture in the atmosphere. And here it's the thermal infrared with the temperature of the surface during the acquisition. The resolution of GOES 16 is only 8 kilometers per pixel, but it's enough for very large scale observation, such as with meteorological satellites. Another illustration of the interest of the different ranges of the electromagnetic spectrum, more applied to land use and land cover. This is a forest to the south of Paris. This is a Fontainebleau forest. You have here the Seine River curse, the city of Melun here, and this is Fontainebleau. And this is to the left, you have the view in the true color range. So in green is represented the reflectance in the green range. In blue, this is the reflectance in the blue range, and in red, it's a reflectance in the red range. So you can see that it's relatively hard to decipher some details in the forest, because the reflectance of the forest in the visible range is relatively dark. You can see a dark green color. The fields, the crops are in white or in pinky colors, or in green if you have some active crops. And the cities are in gray or in blue-gray. Okay, the water is in black. Here to the right, this is the same area using other bands of the Landsat 5 satellite thematic mapper sensor. And in this case, we use the near infrared range for coding the red of the red, green, blue composite, and also the mid-infrared for coding the green range. We will discuss this very important issue of the color composites in other part of the lecture and of practicals, but you can see that it is very different, and it's always necessary for land use, for land cover mapping, to use infrared ranges. And when vegetation is under investigation, mid-infrared and near-infrared could be combined, because you can discriminate between relatively low reflectance. In this case, it's a forest in France. So we have two main types of trees. We have what we call the conifers, that is the fern, this is the pine, the larch, and so on. And we have the decidus, that is the oak, that is the beech, and other kind of trees. And the decidus are in red or in orange, and the conifers are in dark red or in brown. So the reflectance of these two types of vegetation is very different. The problem in Vietnam or in tropical regions is that usually you have forests with a mixture of vegetation, so it's more difficult to discriminate between different kind of vegetation. The forests in France are more or less anthropic forest or artificial forest. So you have planting of different kind of trees. And in the case of this forest, the Fontainebleau forest area, you can see there are very interesting features, such as lineaments. Lineaments is a very interesting notion in remote sensing. These are the line. You can see we have some lines appearing. Sometimes lines correspond to road or to human buildings. But in this case, it's very interesting because it corresponds to alignment of rocks. This is the famous sandstone, what we call the Grès de Fontainebleau, this Fontainebleau sandstone. It is consolidated sand. And these sandstones are aligned, and the origin of these alignments has been deeply discussed by the geologists because it's not very clear if it's of sedimentological origin or if it's due to the tectonic. So it's I think it's a good illustration of the power of color composites integrating the infrared range, and particularly the near infrared for different kind of vegetation, and the mid infrared for the states of moisture and humidity. This is another illustration of the interest of comparison between visible and infrared range. We are here in the Réunion Island. Réunion Island is a French overseas department in the Indian Ocean off the coast of Madagascar. And here is a famous area of Piton de la Fournaise. It is one of the most active volcano in the world. And you can see here flows, lava flows from the Piton de la Fournaise volcano in 2003. And this is a view in the visible. So you can see recent, the very recent lava flow here in black. Very important because it reached the coast and induced a small enlargement of the island. You know, with some hectares gained on the sea due to the lava. But you have also oldest flow. Piton de la Fournaise is very active because you have, in average, you have about one eruption every 1 or 2 years. So you have very frequent eruptions. And using infrared, you can see that it's easiest to discriminate between different types of rocks. And the colors, the different colors are due to two aspects. It is petrology itself, because rocks is a basalt, but it can be slightly different. For example, the fluidity of the lava is not, the viscosity is not the same depending from the eruption. But also, when you have old lava flow, you can have some vegetation growing, kind of mosses or very low vegetation growing on the rocks. So this is an illustration using, in this case, aerial photographs. Okay, other interest of remote sensing is a famous LiDAR. You know, LiDAR is a relatively new approach in remote sensing applications, for example, in in geosciences or also in geoarchaeology. But LiDAR was developed by a forest manager in Canada at the end of the 20th century to estimate the volume of the timbers. So it's a very powerful method because it's possible to have different values. I will discuss further in details in another talk, but it's possible to look at the canopy, such as in aerial photographs. Here you see it's a place very close to Reims with the vineyard. You can see all this gray pattern correspond to vineyards, and this is a small forest. Okay, it's very difficult to look at the land use in that area. But when you use the LiDAR, it's possible to have also a signal reflected by the soil. It is what we call the last pulse of the signal. And in this case, it's remarkable because you can see the shape of a fortification. This was a fortified place because the area was used during the First World War. And this place was occupied by the German, and the German used this place during 4 years during the war. And now there are some people, there is an association working for the valorization, for the attraction of this place, because it's a very interesting pattern and it's interesting for patrimony. And LiDAR can help to look at very interesting features in the rainforest. For example, in Central America, a lot of Amerindian ruins and buildings have been discovered using LiDAR techniques. So the problem with LiDAR is it's relatively expensive to develop, and it's also expensive to process. It's hard to process. During this lecture, I will emphasize the interest of the shortwave infrared because it's a very interesting range in geoscience. And here is just the first illustration. It is one of the places where I worked in the field. It is in southern Madagascar. It is a very dry place, arid area, and very few vegetation. And there are some problems with water supply in this area. So I worked to better understand the reason why a lot of well provides salted water. So it's a problem because you have a few wells and most of them provided salted water. And the geology is very interesting. Here it is simply the view you can look at using Google Earth. You know, it's a visible range. It's very interesting. You can look at some very interesting difference in reflectance corresponding, for example, to vegetated areas. Usually it's a granite rock, such as this elongated area. But when you use color composites with a shortwave infrared here, you can see a lot of discrimination corresponding to different kind of rocks. In this case, you see the rock are aligned in a north-south trend. And if you take one of the curves crossing the different kind of rocks like this using a GPS receiver, and you can look at the rocks and check the nature of these different type of rocks. And you can see, for example, in this case, the blue correspond, you see the blue here, more or less blue, correspond to marbles. These are carbonates, metamorphized carbonates, providing blue colors here. Very typical in this area, but you have plenty of different kind of metamorphic rocks. I will show you other details when we will speak about the shortwave more in detail as well. Among the main advantages of satellite images, you have also, as illustrated by the radar applications in Gabon with the land cover. I show you the interest of using radar in equatorial areas where you have a lot of clouds. This is a comparison between the radar data get in French Guiana area in Southern America here, along a river. The river name is Aprouag River here, Aprouag River. And this is a Landsat data, but I looked at all the archives of the Landsat chronicles, and I find only this data with relatively few clouds. You see, there are plenty of white patterns like this, but it was the best optical data that could be used in this case with a false color composite. You see the red correspond to the rainforest reflectance, and the curse of the Aprouag River is more or less greenish in this case because of the content of iron oxide in the water. So it's clear that the radar is interesting because it is not influenced by the cloud, but it is also more interesting because radar is more sensitive to morphological differences. You can see that this feature, more or less linear feature, is very interesting because it corresponds to an important fault in the field. We have, after some days using the boat, we stop here on the only outcrop, visible outcrop, to measure the characteristics of the fault. And it is a very important fault in the metamorphic series of French Guiana here. You here can also recognize a rounded shape. You see, it's quite impossible to distinguish in the optical data. It corresponds to a small, what we call in geology, a batholith. It is granite, a small granite spot here. So you can see that the morphology is modulated depending from the petrological properties, but also from the properties of the radar acquisition itself, because it depends from the wavelength, it depends from the incident angle of the radar, it depends also from the frequency and from the polarization of the radar signal. So radar and optical. Radar is very useful to achieve some geological mapping in areas such as in equatorial region. Another example, once again in Gabon, because I had another PhD student working in geology on this very nice area. You can see here a very large syncline. This is a Nyanga syncline. Nyanga is this region. It's the name of a river. And basically, the Nyanga syncline is partly in Gabon and also partly in the Congo neighboring country here. And you can see the syncline very clear. You can recognize the area I show you previously here along the Ogowe River. This is more interesting for geology. And this is the old basement of Gabon with a lot of interesting mineralizations. And it's possible to find some metals such as manganese. For example, manganese is deeply mined in the Franceville area in the eastern part of Gabon. This large-scale pulsar data. So pulsar has different modes, and this is a ScanSAR. ScanSAR is a large-scale mode, allowing a very large area to be covered, and with a pixel size of only 100 meters, but it's enough for geological mapping of large areas. But you have also radar mode with 6-meter resolution. And to the right, it is Envisat MERIS data. It was possible to find an area, an acquisition with a few clouds. You can see it's very rare to look at this area of Gabon with a relatively cloud-free sky. So after this presentation of some properties, just a few words about the different type of sensors, because in remote sensing, we have different kinds of sensors and information acquired. We use mainly what we call imager, that is to say, sensors providing an image, a raster file, and the ground space resolution of this image can be extremely different from 50 centimeter to 5 kilometer, for example. And this is an example of very large view. This is the first view of the Earth like this in 1972. It was acquired by the last Apollo mission, Apollo 15. And here you can see, on the contrary, you have a very detailed picture from Pléiades. Pléiades provides information with 50 centimeter resolution. And you can see a famous viaduct. It's a very large bridge for the motorway here, crossing the Tarn River near the city of Millau. And you can see here the viaduct with the piles and the road. So it's very clear, and you can see also the orientation of the sensor. So this was to illustrate the image, the raster notion. But you can also get some topographic data, you know, and the first interesting topographic data were altimetric data. So in the 90s, the first joint mission between France and the USA was named Topex Poseidon, and now we have JSON also. This is a continuation of this first mission. And it was dedicated to the perception of the elevation, particularly the elevation of the sea, by repeated paths. It was possible to have an average value, and so you can calculate at a time the difference between the acquisition and the average value. And the first dramatic illustration of this data was with the famous El Nino phenomenon. You know, the El Nino phenomenon, it's a warm current in the Pacific. And this current sometimes arise very close to the coast of Central and South America, and induce large perturbation in the Humboldt currents. It's a cold current, and the warm water from El Nino deeply disturb this temperature, and there are a lot of problems. For example, for fishing, but also from a climate viewpoint, because the warm periods are associated with rainfall, very important rainfall. So this was one of the first illustration of altimetry. You can also very classically now use altimetric data to draw what we call digital elevation models. And for example, using SRT-AIM or GDT-AIM raster images. In this case, it's a DE-AIM obtained using digitization of elevation curves on a map. It is one of my test sites located in Yemen, to the east of Sana'a, the capital city, and it's a place with interesting old silver mines. This is a carbonate massif, and this is some volcanic areas, and you see the blue color of the carbonate is due to the metamorphism due to the intrusion of the volcanics in the Miocene. So you can see the different shape of the wadis. This is a Wadi Jabali coming from the mine, and it's easier to have a good view of the topography of an area. So this is a very interesting, so I think it's very interesting because it's one of my works. It's an illustration of the use of this digital elevation model on geological issue, and in this case, after a very large earthquake in the Altai, the name Altai earthquake. This earthquake occurred in 2003 with a magnitude of 7.3. It's relatively important. And it was in the Altai region. You see here the field view more recently in 2015. And this is a landslide produced by the earthquake. Fortunately, this earthquake occurred in a very remote area with a few inhabitants. So we have no fatalities, but we have a lot of disturbance in the morphology. And because the earthquake and then the landslide occurred in 2003, I explored the SRT-AIM digital elevation model, because SRT-AIM, you know, probably was get in 2000. The mission of the space shuttle was in February 2000. But the Aster GD-AIM on that area was made using Aster data from 2004. So it is after the event. So I compared the results of a cross-section using the US SRT-AIM you know here the shape with the dotted line. You have here the initial shape with the SRT aim, and after the earthquake and then the landslide, you have the new shape, solid line, with Aster GDE aim, the shape in 2004. And you can see exactly here the place where what we called in hazard management the zone of depletion or depletion zone, with the surface of rupture. This is the age of the rupture of the landslide. And then you have two areas of uplift, because these areas are areas of, particularly at the bottom, you have a zone of accumulation of the product sliding along the slope here. So I published this work with a Russian colleague from Novosibirsk University, Mikhail Buslov, and this was the first illustration of the use of the comparison of these two acquisitions to illustrate an event which occurred just between the two acquisitions. So I think it's nice. And it is what is also very interesting in remote sensing. We have a lot of data, we have a lot of archive, and we have a lot of issues from an environmental viewpoint. So we can monitor this set of data and to find some interesting topics and some interesting goals. So this is the first, this is a seminal work from Didier Massonnet and his colleagues from IPG in France, showing the earthquake, sorry, of Landers. This was in 1992. This is the first illustration of what we called interferometry. You know, interferometry is one very interesting properties of radar remote sensing. Usually we use what we call the amplitude. It is more or less reflectance of the data, but we can also use other characteristics of the signal, what we call the phase. And when you explore the phase part of the signal, you can find vertical displacement corresponding to sequences of displacement, and it is related to the wavelength used. In the case of here, ERS1, it's the C-band of the radar. That is to say, it is the 5.6 centimeter band. And you can see series of colors corresponding to half the wavelength. That is to say that all series of color correspond to a vertical displacement of 2.8 centimeter in vertical. And due to the fact that this kind of earthquake is very important, you can see you have more or less, I don't know exactly, maybe you have 15 or something like that. So you have a displacement of about 50 or 60 centimeter. And sometimes it could be 1 meter, 2 meters, 3 meters, and so on. But this is the area of the central part of the Landers to the north of Los Angeles, of LA. And this was a very important earthquake, but not the big one. You know, it's a very dangerous and hazardous area. Another illustration, and it's not so spectacular, it's not so important, but it was an earthquake in France in November last year. We had an earthquake in South France. This is a Rhône River. This is Montpellier, Montélimar, sorry. This is Montélimar. And here on the right bank of the Rhône River, you have a small town. The name of the town is Le Theil here. And in Le Theil, we had a small earthquake. Sorry, I put this one. The magnitude was 4.9, so it's relatively low for an earthquake, but in France, it's very rare to have such a quake. And interferometry has also been applied. You see there are just a few series. In this case, it is the same wavelength. It's not the same sensor, but it's the same wavelength, the C-band. So we have 1, 2, 3, 4, 5, something like that, 5 series. So the displacement is about 12 or 15 centimeter, but it was sufficient to destroy some houses and some walls, and particularly the church, for example, with a relatively high tower. So this was the first interferometric results get on that area by colleagues from Montpellier and others. Okay, these are different intermediate products. This is the amplitude, and this is a coherence. It is a difference between two data. One acquired the November 6 before the quake, and the other data from November 12, just one day after the quake. And this is very important to look at what we call the coherence between two images. I do not explain further in detail because it will be necessary to spend 1 or 2 hours on that kind of explanation. But you see, this was a first results, but now I had this new results. It was published in August this year, and this is better. And this emphasizes the role of faults along the Rhône Valley. We have a lot of faults like this, and these faults deeply disturb the area. Topographic data can reach also to digital elevation model using LiDAR technology. One of my other PhD students worked on the Mont Saint-Michel Bay, and she can use at that time the first LiDAR acquisition due to the Total Foundation. And we get this digital elevation model on the bay, and difference in elevation between the higher and the lower points is only 20 meters, not more than 20 meters. Okay, other illustration of the LiDAR here in a forest in Western Germany, in the Bad Württemberg area. You can see here the forest with the first pulse. Amplitude here is emphasized, and here it's last pulse, the last pulse corresponding to the soil. You can see this feature, for example, this is a kind of trough. And also what is more interesting in this case is you see the pattern. You can see the old crop pattern corresponding to a pattern of the Middle Ages. Because after that period, this area was abandoned and particularly during the 30 Years' War in the 17th century. So it's possible under the present day, the current forest, to see some interesting features corresponding to the former land use. This spot corresponds to bombing during the Second World War in this case. Okay, other illustration of bombing. Here you can see the forest and the results of the last pulse. And here we can also look at different kind of bunkers, craters of bombs, and also some trenches, but the trenches during the Second World War was relatively small compared to the trenches during the First World War. We have also devices acquiring geophysical signal. In this case, we do not use the signal in the visible or in the infrared range, but in other ranges. And it is interesting, for example, in this case, to look at the magnetic field as observed by a satellite of the European Space Agency. The name of this satellite is SWARM. You can look at the signal at the Earth's surface. Red color corresponds to high magnetic areas, and blue colors are relatively low magnetic areas. You see Vietnam here, relatively high. It's similar, more or less similar to southern France. You see you have a yellow color for Vietnam here. It's not very magnetic. And you know that magnetism is mainly related to the poles, to the magnetic pole. So it's mainly concentrated to the north and to the south, but not exactly to the geographic poles. Okay, in geophysics, we have sensors dealing with magnetism, but also with gravimetry. Here, this is another sensor from the European Space Agency. This is GOSI. It means Gravity Field and Steady State Ocean Circulation Explorer. And Earth's gravity is then measured, and it's very interesting because you can see the relation between geodynamics and the signal. Especially you see the Andes here and more or less the Rockies in the North America, but Andes, it's very clear with the subduction area. And you have also the Alpine chain, the Alps itself, but also the Anatolian belts and Central Asia belts, and the Himalayas, and also Indonesian areas with the subduction in that area. So it's clearly related to geodynamics. So this is this map. These maps are generally the synthesis of a few years of acquisition of the signal. This is another probe monitoring the ozone this time. This is a GOMOS sensor. This sensor was on board the Envisat platform, but unfortunately, Envisat is no more in operation since 2012. And this probe called GOMOS is a Global Ozone Monitoring by Occultation of Stars. It's a very efficient tool to measure the rates of ozone in the atmosphere using particularly spectral band at 9.7 micrometer. And you can see here a view of the Antarctica area, the South Pole. This is South America, sorry, South Africa here, and Australia, New Zealand. And in blue, you can see depleted areas. That means areas with few ozone in light blue, or more important in dark blue. So these are different acquisition. This is September 8, this is September 15, September 22, and this is September 29. So you can see that the area is always depleted in ozone, but sometimes the depletion is more important. So it's very frequent, it's a well-known phenomenon, it's known since the 1950s. There is a depletion of ozone, particularly in September and in the South Pole area. But we have also depletion in the Northern Hemisphere, and sometimes influencing also Europe. So, as I mentioned to my students here in France, but I think it's very important to have in mind that we have now a lot of satellite data available. Some of them are very classical. You can look at these images on the Google Earth, but you can also relatively easily download Landsat or Sentinel data. But we have also some aerial photographs, and these photographs can be very useful. During my work for geological mapping in Normandy in France, I use a lot of aerial prospection using some interesting dry period, for example. And in this case, you can see the parcel here. And this was probably wheat area. And in this view taken in September, you have no more cereal crops. And you have only some grasslands, some small plants growing along the fault here, because the fault is a relatively humid area. You know, it's this fault affects very hard limestones, carbonate rocks. So we have the fault itself with a relatively complicated pattern, what we called in geology a riddle, you know, with a kind of relation between this part and these other parts. This is not only one fault, such as on a geological map, but you have a very complicated pattern. And so during a few days, you can have some grass growing in these areas due to the moisture and humidity. So it appears relatively dark in the image, and not such as the other part. You can just have a small idea here of the boundary of a rock bank here, but it's not very clear. You have also another pattern here, but I do not explain all this in detail, but you can imagine that when you are in the field, it's quite impossible to look at this pattern because usually it's not visible. And even if you are at a good period, it is not possible to look because the scale is not adapted to the view in the field. So I took benefits of one of my colleagues, Patrick Gigot, who was assistant professor at the Caen University, and he was a pilot, and we use frequently his plane for aerial photographs, for example, for geology or for geological hazards along the rocky coast, for example. This is another example for during the same mission. You can see other geological features. You see here some faults. These faults are more regular than the previous faults. You can see also difference between yellow area corresponding to more or less outcropping limestone, and the green area corresponding to marl with some clays. So the rock is not the same. So this is geology, but you can see here that there is also other features corresponding to these lines. And these lines are interpreted by the archaeologists as a trough. This was the boundary of some area for cattle, for concentrating the cattle, and mainly for concentrating the animals here. And what you can see is only the track of the troughs. And sometimes it's possible to find in the field, when there are some excavation, it's possible to find some other artifacts. But this is due to the human, and this is due to the nature. You can see here, this is the wing of the plane. Okay, and because we are in Champagne, we have a lot of track of the First World War, because Reims was just on the front line during 4 years. I already illustrated with the fort of Nogent-l'Abbesse and the LiDAR, and here it's an aerial photograph. This time it's not me, it's not from me, but from a colleague from Champagne, Michel Gérin. And you can see here the famous shape of the trench with irregular shape to avoid the line, long line. And this was a trench. This was, in this case, a French trench, but sometimes the trench were occupied by the German and sometimes by the French. Only it lasted 4 years only to get some tenths of meter. Okay, just before a second break, I would like to say a few words about the famous virtual globes. I already mentioned Google Earth. Google Earth is a very interesting and powerful tool, but Google Earth offers some limitation, and I would like to emphasize these limitations. You have only data in the visible range, and I think that I have illustrated that other ranges, such as infrared or the radar ranges, are very interesting. So in the Google Earth, you have mainly visible. You have only, not mainly, but only visible range data. Generally, you have recent views for the high accuracy. So it's very interesting if you are dealing with the study of a city, for example, if you are studying Hanoi or Ho Chi Minh Ville, it's interesting to have the recent view. But if you are trying to study the land cover of an area, it's necessary to have more larger images and not necessarily very recent, especially for geology. It's not necessary to get the more recent data. You have also only vertical views, and I show you some oblique view, and oblique view can be of better interest related to shadowing of the object in the field. For example, the trenches, the previous trenches here, you cannot see here with a vertical view. It's very difficult. And it's only due to the fact that this photograph was taken at the good moments from a seasonal point of view, but also from a daily hour viewpoint as well. So you have only very high resolution images. So once again, it could be interesting if you are using, for example, erosion in an area of coastal places. It could be interesting because if you have very high resolution images, you can quantify erosion or sedimentation. But very high resolution image means very large raster files, and it's sometimes complicated to use and to interpret. Also, you have mainly the urban areas covered by a large amount of data. And if you are looking to, for example, some areas in the Saharas or in the Amazonian forest, maybe you have no high resolution data for these places using Google Earth. And the last remarks I would like to emphasize is that note that Google Earth image does not exist. Google Earth is only a trademark, and Google Earth concentrates images from different agencies and companies, and such as Spot, Pléiades, Iconos, QuickBird, GeoEye, Landsat, and so on. So it's always necessary to find the good reference of the image. So Google Earth image does not exist, but Landsat image exists, Pléiades image exists, and so on. So sometimes it's very difficult to know because when you are consulting the metadata, they are useful, but usually it is indicated only the commercial network and not the sensor itself. For example, if you have a Pléiades data, Pléiades image, it is not written Pléiades when you are consulting Google Earth, but Astrium. So Astrium is a private company dealing with this industry of commercial image. Or Digital Globe for the American data is used, for example, for QuickBird. So you have also, for example, CNES is indicated for Spot and so on. So it's necessary to know exactly what is represented. So Google Earth is very interesting, but unfortunately, I think that the actual potential of remote sensing is not totally demonstrated. Okay, this is, I do not comment in detail this sketch, but this is, I published a number of times this kind of sketch representing the different kind of sensor. Since the first sensor, you know, in the 1960s, you have some interesting sensor with the spy American satellites, Corona missions at about 1.6 meter resolution for the best. So it's interesting. But the development of remote sensing is mainly from 1972 onward until the present. And now we have a resolution of only 31 and no 25 centimeter with different kind of sensor. What we call very high resolution is a resolution higher than 2 meters. That means in value lower. You have, for example, 50 centimeter. It's a very high resolution. High resolution between 2 and 20 meter. So you can include most of the spot satellite, for example, or Sentinel satellite, and middle resolution for the Landsat and also MODIS and so on. Okay, so I do not detail all the sensors. Some of them are not necessarily widespread, and it's difficult to have information about them. But others are well known, such as Landsat and now Sentinel data, because these data are very easy to find and download. Okay, I think that it's time the goal, basically the goal of remote sensing is to get some map or information, but usually it's possible to have general information, such, for example, two illustration of remote sensing use, for example, in for geological mapping. Here you have a spot image, okay, and this is the results of the analysis from a geological viewpoint of this data. This is the data on southern France, and this town is Montpellier here, and this is the Mediterranean Sea. But if you are interested by forest, you can also make another map of the forest, because you have different type of trees, okay? If you are interested by transportation, you can make a map of the different tracks, motorways. You have motorways, you have small roads, you have train, you have also other type of ways. So you can derivate a lot of different thematic map using the one data. This is an example with optical data, but you have also here an example with the radar data. This is in the case of the French Guiana, the area here, and radar is very powerful for drawing geological map in an area which is very difficult to investigate in the field, because you have a lot of trees. It is a rainforest, so it's very difficult. But it is also important to have in mind that the radar data alone is not necessarily enough for drawing a very good geological map or thematic map. So field data and other data, what we call exogenous data, are always important to know. This is an example of the very high resolution in geology. You see these are carbonate layers with dolomites and limestone in Yemen. This is an aerial view of the same area, you see, and this is the result using QuickBird data, very powerful. Dolomites are more generally in blue, and carbonates are in white or in pink color. And this particular feature here is a vein of volcanic rocks. You know, it is crossing the geological series, and here is a small fault with a short displacement along this fault, but it is possible to perceive the displacement when you are looking in detail. So this is another example of very high resolution work in Egypt with archaeologists in the Eastern Desert. It is the area between the Nile River and the Red Sea. And in this area, you have old gold mines. You see it's in the Beer Summit area of the Eastern Desert. And these are mainly granite rocks, and you can see the all these places are old mines during the antiquities. So as a conclusion of this first survey of remote sensing, we have a number of satellites, but the acquisition and the processing of the data is or are frequently difficult because it's necessary to choose a good data. Sometimes you can have some cost problem because the interesting data could be very cost a lot of money. And sometimes also we have issues with the software because we have not the good software, we have not the good version, etc. So it results in science as a whole in an underutilization of satellite data in geosciences and all the sciences around the environment. So sometimes people are working, I know, for example, biologists working in areas with no satellite data, whereas satellite data could be very interesting. So it is very important to know the potential of satellite data. We have numerous data. Also, we have a lot of data, but frequently these data are not necessarily appropriate in scale, spectral range. I mentioned the case of Google Earth, for example. Also, we have some problem with the revisit time. That is to say, the time between two acquisitions. If you are looking at a very dynamic event, such as a volcanic eruption or a flood event, it could be necessary to have very regular data. And if you have to wait for 1 week or 2 weeks between two data, so it is quite it is not interesting and not possible to use. And also, and I will illustrate later on this problem, there is also sometimes local time of acquisition problem because you know that satellite data are more or less acquired in the same time conditions, temporal conditions, and sometimes it could be not adapted for example, coastal areas, but also if you are working, for example, in in pollution in some cities, because pollution is usually higher in the evening or in the afternoon or evening, and acquisition are usually in the morning. So if you are, for example, working on Hanoi, it could be interesting to compare the setting in the morning and the setting in the evening. But right now, with most of the satellites, it is quite impossible because there is no dedicated missions with comparison of data 3, 4, or 6 hours after the first acquisition. And also, we observed a relative complexification of the database. We have products that are sometimes inadequate for the thematic purpose, high potential of remote sensing, particularly with the LiDAR and spectral high resolution. But spectral high resolution, I will discuss spectral high resolution later, but spectral high resolution is very difficult to process, for example, and LiDAR also is not necessarily easy to process as well, because it's necessary to have a very good acquisition with a very stable platform, with a plane with not a lot of perturbation. So, for example, in tropical areas, it could be more difficult to acquire good LiDAR aerial or airborne data because of the atmospheric conditions, and sometimes with humidity, and sometimes with other issues. Okay. This was the end of the first called brief introduction to the interest of remote sensing. The next part is the basic definitions in remote sensing, but I will start this part tomorrow morning, okay? And I would like to dedicate the end of this of the present presentation for introducing the practicals. So I will stop to share right now, and I invite. So I will show you some basic information about Envy, because I don't know what is your knowledge of the software. Do you already have practice of it? It's in eastern France, you know, it's a small village in the vineyard of Alsace. So
we cannot see the desktop. We just see the
tool. You have only the toolbar. So you have my you have my screen in the background. It's not very important right now. So you see that Envy is composed of a different kind of items, so-called file. So file is important to download and to launch with the different file you have selected. So we will discuss the main interesting sub-items. So item basic tools, as indicated, these are all the basic functions in digital processing. That is to say, resizing the or selecting an area. It is also interesting for what we call layer staking, that is to stack, to put together different bands of an image. And what is important right now is also statistics. Statistics is a very efficient tool, because what is interesting in digital data is the use of statistics. That is to say, you have to know what is a value in digital numbers, so you can convert the digital value in reflectance if you have some possibility to calibrate the data. And also very important, I will show you the region of interest tool. because in an image, you can monitor the image as a whole, but the image is not enough if you are looking, for example, to vegetation, or if you are looking to geology or to water bodies. So you have to find the possibility to select some areas of interest. Mosaicing is interesting when you have to put together two different images with a common area. So you can have a larger image with all the area concerned. We will also explore the terms about classification, and I don't explain now the difference of classification because this is only dealing with the basic function. But you know, in classification, you can have what we call unsupervised. That is, the classification is made by the computer, not by you, or using your own information. Or supervised. Supervised means that you are able to select a number of classes with the meaning of these classes. Okay, I see that one want to enter, I admit. Sorry, I have some admission to do. I think it's okay like this.
It's okay.
Sorry, I have to continue. So I was in classification. So classification, supervised, unsupervised, we will discuss later on. Transform, it is also interesting, and particularly you have function such as the famous NDVI. It's a normalized difference vegetation index. It's an index used for mapping biomass, vegetation. Filter is more dedicated to radar data or images with texture. Spectral is relative to, for example, some corrections such as the famous flash procedures. But I think we have no time to explore these sub-items. What is interesting is map. Map is more interesting because map allow you to georeference, for example, or to correct an image relatively to the coordinate systems. So it could be interesting to change the coordinate system or to apply a coordinate system to a matrix, to a raster matrix without georeferencing. This is a case, for example, with the Sentinel-2 data. It's necessary to register, to georeference the data before stacking the different files. So vector, as indicated, is dedicated to vector file monitoring. Envy is not really a GIS software. It's a very powerful image processing software, but you have some function, and you can also convert, for example, raster to vector and monitor some vector file, shape files, and so on for selecting, if you want, for example, the statistics using an administrative area. You can use a shape file corresponding, for example, to the different district or province in Vietnam, and you have the statistics by district and not as a whole. Or you can make your own boundary, for example, with natural areas. Topographic is interesting when you have digital elevation models, okay? So it's interesting for combining an image, a raster image, and digital elevation model, or to extract information from different type of data. But here we cannot see all the sub-item because it's a very powerful. For the radar, we have specific tools such as the polarimetric tools. You will understand after the lecture, because I will discuss about the characteristics of radar, and especially you have the polarimetry. It is a very important aspect of radar image. Window and help are classical windows and information. I think it's not very important right now. So I prepare an image. So I expect that there is no problem. If you want to enter new files, you have to select either open image file. If the format of the file is a classical format, such as GeoTIFF or JPEG format, but you can also sometimes use open external file. You see, if you put external file, you have directly different type of image with specific formats. You find again, for example, for Landsat GeoTIFF, so you can open with open image file directly, but you have also HDA phone or MRLC format. It depends from the format of your the data you use. But if you download the data from the USGS website, for example, from Earth Explorer, from the USGS in the United States, it's not necessary to go in this window, but you can open directly using open image file, because it's a GeoTIFF, and GeoTIFF is recognized by the software. But sometimes, for example, what is particular here, for example, ALOS. ALOS, it's a Japanese satellite. You have PRISM for the panchromatic sensor, Avenir 2 for the multispectral, or PALSAR for the radar sensor. In this case, it will be useful and necessary to open the file using this specific function, because it's a dedicated format and it's not widespread format. So it is detailed, but sometimes it is very useful for loading some data. I go back to open image file. So I click on open image file, and I prepare in my, here in the download, I prepare a file named Sentinel-2, you know. I prepare a subset to have just a small area of a place. I already show you the Bay du Mont Saint-Michel, okay? And you have to select the image, okay? So you can select, for example, here, I prepare in the Sentinel-2, you have 3 types of resolution, 10 meter. Yeah, sorry, Tang, you have a question?
Yes, because now we only see the very small window, and we cannot see the file in that. So,
okay, it's probably because I am looking for the file on my computer.
Yes.
So maybe when it is loaded, it is correct. We have to check. Okay. I select, but no, I don't see the. Okay, I open. Is it correct? Do you see the available band list?
Yeah,
Here, in the middle. Do you have the available band list? No?
no, no. Only the menu.
Ah, okay. It's really a problem. It's a problem because I don't understand. I can try to, and here, do you see something different? No, I enlarge the window, but it seems it's not this. Ah, okay. So if you don't see, it's not possible because I share my screen, but I don't understand why. Ah, okay, I understand. I understand. Maybe there is a. Okay, so sorry, it stopped. The screen sharing stopped suddenly because I tried to. I try again. Okay, I understand. At any moment, I have to. This time, probably you
Yes.
see
The list.
but I have to change systematically. I have to change the window. You can have a look at. It's very complicated because for the
Is there
video.
Is there any option that you can share the whole screen? Then you don't need to move to change it.
I don't know because this is the first time I try to look at Envy using a video. So because this is not very interesting. So just a moment. I made a color composite and I look at the results. I suppose that you cannot see the color composite. You only see the available band list. Yes, okay, it's really a problem because I have to change. Where is it? Ah, okay. Ah, okay. Because I can only share one window at a moment. This is a problem. And I cannot generalize. Okay, this time you have the, probably you can look here. Okay, you have the image, I think. It's correct?
Yes.
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 But yes, okay, but there is no more the. So I think that I have to prepare another introduction to Envy, because like this it will be very difficult. But I can show you here the area. And I choose only the visible range of the sensor. That is to say that in the red, green, blue color composite, I use the red range in red, the green range in green, and the blue range in blue. Okay, so the results is here. And you can see the area under investigation. I display slightly. Okay. So this is this area in the western part of France, and you have here a small, very small island, because the width is only 800 meters. It's the famous Mont Saint-Michel with an abbey at that place. It is a smaller island, so-called Tombelaine Island. And here are the land. And you have rivers, the Sea and Sélune rivers, and to the south, it's the Couesnon River. Here in the bay. And you can see here an image in the visible range, but it's very difficult to know whether the water is high or not. And I will show you just for illustration, because I think I cannot change the window for you, but I change only the composite, and this time I only choose bands in the infrared range. Red is a near infrared, green is a short wave, and blue, sorry, it's very long. No, it's not the good one. It's very low. It's very slow. Okay, this time, you know, I think that images change for you. Probably it's okay. It's correct. Okay, so it's just for illustrating the fact that you know here all the black areas correspond to water. So the elevation of the water is relatively high because the water is here. And using the other composite, it was quite impossible to distinguish. So the capability to compare two. So I change just to show you the difference. I expect that it could work. New display. Okay, so it's very complicated because I have indication on my different windows. So I think it's not adapted to the video. I will try to share window, maximize open display. Okay, no, I cannot use the maximize open display function because the sharing disappears. So it is not possible for me to show you the difference between the two windows. So I just, I go back to the, no, not to scroll. Okay. Okay, I think that it will be difficult because we have 1 hour for this, and I think it's not very easy and not pleasant for you and for me as well. What? I am looking for the properties of the sharing, but I don't see the. No, I think it's quite not possible. So I think it's not very easy. So I prefer to stop this first presentation. I show you just the illustration of the main function. You have to load the data, and I will send to you a link or directly the files for downloading, because the files are not very important. I think that the files, each file is only 2 megabytes, so it's relatively small. So I will send to you the files, okay? And you can try to prepare some color composites by yourself. I think it will be better, but I provide you with some information, because other information will be delivered tomorrow morning. So no, it's okay like this. Nouveau partage. Alors, where are the band? Okay, I think that now you have only the available band list. Okay. So you see band number 2, number 3, number 4, number 5, 6, 7, 11, 12, and 8. It's relatively complicated because you have other numbers, 1, 9, and 10. But 1, 9, and 10 are bands only at 60 meters, so it's not possible to use with the other bands. You have band 2 is a blue range, okay? You can check using the Sentinel website or Wikipedia. It's very easy to know the corresponding bands. You have band 2 is the blue range, band 3 is the green range, and band 4 is a red range. So if you are playing a true color composite, you indicate, as it is mentioned here below, in red, you indicate, you click on band 4. Okay, you have band 4. This is red range. In green, you click on the band 3, that is to say the green range. And in blue, you have the blue range here at 20-meter resolution. So when your composite is correct, you click on load RGB composites, and you obtain a new window with your image. But unfortunately, it's difficult to show you the results because I have to switch from one window to another window. What is important, so I can, okay, yeah, no, a new problem. What happened? A new problem. So I try to show you. You have the first window. Okay, the first window you get is what is called the scroll. You know, when you launch the image, when you load the RGB composites, you have 3 levels of observation. You have the scroll. The scroll is a representation of all your scene, whatever the size, and the red box correspond to what is indicated in the visualization window, okay, of that area. And you have also another visualization mode. It is the zoom mode, but the zoom is located on the visualization window. So I change now I share with the grayscale. I expect it's correct for you. In this case, okay, you have the, I can just, okay. This visualization window is a second window, and you have also here a red square corresponding to the zoom area. You can displace by clicking on the red square, and you can go, for example, on the coast. And when you are looking to the zoom window, sorry, I change once again. I share now with, where is the tool, the zoom? Okay, this is now the zoom window. And this is the area, oh, sorry. Okay, probably you have the zoom. You can see the zoom is a very small area with a pixel. You can recognize the pixel, but I put the selected areas just at the border between the continent and the sea and the bay. And so you have an enlargement with the zoom, and you can put, for example, detail for each pixels. So it's not always interesting to use the zoom window, but if you have very small areas, such as one specific tree or one place with specific rocks, it could be interesting to use. Okay. So I go back to the available band list. Where is? Okay. So 2, 3, and 4 are the visible range, blue, green, and red, respectively. I jump to the 8A. 8A is the near infrared range. Okay, 8A. You have also the data 2, 3, 4, and 8 are also available with a resolution of 10 meters. If you download the Sentinel-2 data, you have the file with a better resolution, that is to say 10 meters. But in this case, I prefer to use these 9 bands because we can combine with the infrared range, with different infrared range. Number 5, 6, and 7, it is a property of Sentinel-2 sensors, so-called MSI sensor. You have 3 bands in what we call the red edge. I will explain you what is the red edge. It is a transition between the red, okay, the red range, and the infrared range. So it is an area where the reflectance of vegetation deeply increase from about 10% to 50%. So this area is very interesting for studying vegetation. Okay, this is 5, 6, and 7. This is very particular. You have not this range on the Landsat thematic mapper, for example, or OLI. And after that, you have more classical bands. Number 11 is mid-infrared. And tomorrow I will explain you what is the interest of this range. And 12 is a shortwave infrared. I already mentioned the interest of the shortwave for geology, particularly at 2.4 micrometer. So this is band number 12. Okay, so and I just illustrate one property of water. You have seen that water has no reflectance or a very, very low reflectance in the infrared. So I propose you for tomorrow morning, you can try to do some color composites, and I will prepare the composite and introduce the composite in my presentation, so we can look at the composite without any problem, because with the software it's very hard to combine visualization of the different windows. And maybe I will find a solution. I will solve the problem of sharing the screen with different windows, but I am not optimistic from this point of view. Okay, this is these are okay. You have question?
Yes. Sorry. You will give us the data, or we need to download the images to try?
Sorry, I cannot understand what you mean. I heard very
because you asked to try the RGB images, but you will give us the image, or we need to download it?
Yes. I will send to you the files just after the course. I prepare the files and I sent you. I think that it's possible to be sent using maybe two messages, because it's relatively small. It's only 2 megabytes for each bands, and there is 9 bands, so you see it's relatively small, and it will be possible using directly the mailing. Okay.
Okay, thank you.
So we will discuss after. You know, in remote sensing, we have the true color composite. It is therefore the 432, but take care This is for Sentinel-2 only, because if you use another satellite, number of bands are different. So you have to take care and to use the good band. For example, with Landsat 4, the blue is band 1, but in Sentinel, the blue is band 2. Okay, and for example, with Landsat, band 7 is a SWI range, and here with Sentinel, it's band 12. So please try to do some color composites for SWI2 for the true color, but introduce also the false color composite. It is only using the near infrared range as a red band. You can also make the color composite using the red age bands, okay, 7, 6, and 5. Have in mind that number 5 is relatively close to the red, and number 7 is relatively close to the 8A, to the near infrared. So you have a transition, and we will discuss about the values and related to the bands. So I don't know exactly what is the best now. I am not sure it is. Sorry, it is not so good. Where is my? Just a minute, please. Okay, never mind. I think that it's better that I go back to the presentation, because with Envy right now, I think it's very chaotic and not very interesting. Please made a job with the bands, with the files I will send to you, and try to do something interesting, and we will discuss tomorrow morning this practicals. So I stop my presentation with Envy, but I go back to so wait for a while. I'm looking for the. Okay. I share the screen. Okay, I expect now it's correct for the screen is okay.
Yes.
Okay, thank you, Emma. So I continue with the second chapter. And the second chapter of the lecture is, so as I mentioned previously, basic definitions in remote sensing. So we will continue remote sensing generalities. So human beings, you know, have always imagined the landscape as it could appear at distance by what we call bird eye. So here is, for example, a fortified place in eastern France, in Alsace region. And you can see the geometrical shape typical from the 17th century. And basically, remote sensing is at the crossroad of three major inventions. The photography, it is an invention from the first half of the 19th century. Second, aeronautics, and the progress of aeronautics were important at the end of the 19th century and the very beginning of the 20th century. And last, the propulsion, and propulsion has been improved only in the middle of the 20th century. Some more details about photography. You know that a lot of scientists try to fix an image on a paper, on a product. One of the first was Leonardo da Vinci. But the first photograph is attributed to Nicéphore Niepce. It's a French guy in 1827. And here you have one of the first photographs taken from Le Gras at Saint-Loup de Varennes. Saint-Loup de Varennes is a small village very close from Chalon-sur-Saône, the capital city of one French department in the center-east of France. And Niepce, you know, the French name is relatively complicated. It is Niepce, used a polished pewter plate covered by the so-called bitumen of Judée. It is a kind of petroleum derivative, so it was a kind of bitumen, but it was very unstable. And after Niepce's death, it's relatively rapid, unfortunately for him, because it was in 1833, only 6 years after the invention of the process. And one of his collaborators, the name is Daguerre, continues the work and developed particularly what we called the daguerreotype. It is the first type of image fixed on a solid support. And this is one of the famous daguerreotype representing one road in Paris, the Boulevard du Temple, in 1838. It is interesting because it is one of the seminal photographs taken in Paris, but it also taken before the fitting of the city by Baron Haussmann during the Second Empire in France, during the period of 1860, about 1860, 1870. And we have a view of Paris before this, the rebuilding of a lot of parts, particularly in central France. And okay, I continue the small story of photography. One also well-known scientist, François Arago. Arago was a physicist, and he worked with the French government during the last period of the kingdom. And he announced in 1839 the public disclosure of the pioneering photographic processes. This is important to know. It is a stamp commemorating the first century of the invention of the opening of the process, not the invention, but the opening of the process. And in 1858, the first aerial photograph, because this is our aim, it's mainly aerial photographs, and the first was obtained by a guy with a relatively strange name, Gaspard Félix Tournachon, but his surname is Nadar. And now, from an unmanned balloon, he acquired at about 80 meters above the soil this picture of near Paris, a place known as Petit Clamart, but at the time of the acquisition, the place was named Petit Bicêtre at that time. The name changed during the 20th century. So after that, the first image acquired by a man in a spacecraft is attributed to a Scottish meteorologist named Archibald in 1882. Unfortunately, we have no, it is funny, but we have no photograph of Archibald preserved, so I cannot show you the face of this guy. And the process by which it was possible to get some images from spacecraft was developed by a French Arthur Batu, and especially Batu developed a lot of photographs in the Alps. Here you have the Mer de Glace, the ice sea. It's a famous glaciers in the French Alps, Mont Blanc Massif. And here is also one of the first famous photographs taken by man. It was after the earthquake in San Francisco in 1906. So the city was totally destroyed. It's not easy to look at the destruction, but all the buildings were destroyed in that area of San Francisco. Fortunately, at that time, the city was not so inhabited than now, but San Francisco and LA as well are also endangered by the famous San Andreas Fault. The first photograph you have seen were only in black and white or gray level, because it was a sensitivity of silver halide that were used. But in 1861, a British physicist, Maxwell is well known because we know the electromagnetic waves of Maxwell. He demonstrates for the first time the additive synthesis of the color using three what we call magic lanterns with red, green, and blue filters. So it's the first use of the red, green, blue color composite. And it is due to Maxwell. And this is one of the first color picture. This is a photograph from a simple ribbon here, get by Thomas Sutton using the Maxwell's method. Very early, scientists tried to find also improvements of the color process, and two French guys, Charles Cros here and Louis Ducos du Oron here, developed a new process, what we call now the subtractive methods or subtractive methods. This is indirect color photography principles. And here in 1877, this is the city of Agen in southwest France, shot by Louis Ducos du Oron, born in this small city in southwest France, along the Garonne River. Others tried a very complicated process, such as this guy, Gabriel Lippmann. He was a member of the French Academy of Sciences, but his process has no future because methods was too complicated, too complex to improve, especially in the field. And you see in 1912 here a very nice color picture taken in Siberia by Prokudin Gorsky, a guy, a kind of journalist working in Russia just before the Russian Revolution. And some pictures are very nice, but necessitate a long time to be acquired. Therefore, the water is very fuzzy because of the movement of the water. But colors are very good. After this negative experiment by Lippmann, two guys, well-known guys, because the Lumière brothers are well-known because they first developed the cinematographic process, and they deposited a first patent about photography and color photography in 1903. They were from the city of Lyon. And after, color photograph developed by the American first in 1935, the Kodachrome film was invented. Very easy to improve in the field, but with not very good color. And the German invented the Agfa color film as early as 1936. And this color photos, or Farb photos in German, this process is better and the color are of higher quality for this first film. After the Second World War, the Kodachrome film was deeply improved. What about the infrared? No, I speak about black and white and color photographs, but only in the visible range. Very early, scientists tried to get information in the infrared range. You can see here a recent comparison taken from a plane of the visible and the infrared range for an area named Old Hickory Lake. Hickory is the name of a tree in American. It's what we call the white walnut in French, but it's not exactly the same walnut that we have in France or in Europe. Infrared range, it was impossible to use the same system because the silver halides are only sensitive to the visible. It is interest for the first development of remote sensing, but silver halides cannot be used, so it was necessary to use other chemical products for fixing the infrared response in the film. So this is a small history of photography. After we have development of the film, even using rockets and, for example, shuttles. And since 1972, digital records is the rule. And now we have only, for sure, digital registration of the image. So this is for the first point of the ternary photography, aeronautics, and propulsion. So for photography, these developments were very useful. Second, aeronautics. Officially, the airplane has been invented, you know, probably in 1903 by the Wright brothers. It is attributed to the first flight of the Wright, but from the end of the 19th century, we have a lot of attempts, for example, by Clément Ader in France, and Ader invented and coined the term avion in French and aviation is derived from this word. The region of Reims is famous because in 1908 we had the first flight by Farman on a significant distance, about 30 kilometers between Bouilly, not very far from Châlons-en-Champagne, and Reims. So it's a very flat area, so it was relatively easy for this flight, such as in the Thomas flight here with a crash when landing in Issy-les-Moulineaux. It was a famous event because during this meeting, the plane crashed into the officials, so some ministers died and other people in that occasion. And not very far from my office in Reims, when I say not very far, it means about 50 meters from my office, we have here a plaque commemorating the Farman flight. No, it's here that Henri Farman, has benefits of the first flight between two cities. And this is the front page of the Scientific American, illustrating the flight by Farman. It was not very high. It is only 20 or 25 meters above the surface, but the landscape here is very, very flat. And but the first aerial motion picture is attributed to also the Wright brothers, but in Centocelli in Italy, because the Wrights work for the Italian army, and Italy was the first country interested by plane and by sure from plane, even before the First World War, because Italy used plane bombing during a war in North Africa during the Libyan area. It was in 1911 or 1912, something like that. So for France in 1909, the French army speak of aérostat, balloon, airship. Here it's one of the first plane. The Air Force was created only in 1934 in France. In only the British Army during the First World War defined a true Air Force, and in France, Air Force was divided between infantry and other type of land divisions. Aeronautics have a lot of development during the First World War. First, as air reconnaissance, because it was easy to look at the different position of the army, because the army were relatively stable, and mapping the theaters of operation, as we say. And here you have a very dramatic view of a region of Passchendaele. The Passchendaele is small in Belgian Flanders, here close to Yper, and Passchendaele totally destroyed between June and December 1917. Here's a village with some houses, a road, and crop parcels, and this is the result after the bombing. You only recognize some ghost road like this, and you have sometimes more than one bomb per square meter. This is the location of this place. And here you can see Reims. Reims is in the middle of the front line, and the front was stopped here during 4 years. Here is a mapping of the trenches. You have seen a trench using modern aerial photographs, but here you can see a French photograph of the trenches in Mont de Sapignol. It is close to Berry-au-Bac, and it is known as Côte 108 in French. It means that the elevation of the hill was 108 meters, and now we have only 91. After the war, the hill lost 17 meters in elevation. And here the trenches are very well defined because the substrate is chalk. You know, it's a white carbonated rock with a few soils. So it's very easy to see the shape of the different trenches here in Mont de Sapignol with French and German trenches. Another example with German photographs in the area of Verdun. You see the shape of the trenches. And here is an oblique view. It is a British photograph taken in a Picardy area. It is in the north, to the north of France. And here it's unfortunately the illustration of the first use of toxic gases. And the name hyperites, hyperite in French, came from the city of Ypres, hyper in the Flanders language. So this is two planes collisioning. And this is an illustration of the use of old photographs on a fortified place, Fort de la Pompelle, close to Reims. And this fort was occupied by the French. And German tried to invade, but didn't succeed. And this is the evolution of the place. This is a German view of 1918, but this is an aerial photograph of 1949, 1967, 1982, 201, and 212. You see the evolution of the area. So aerial photographs are useful for as image of the past, but also to follow the evolution of site and landscape. We now are at the transition between aeronautics and propulsion, the third aspect. During the Second World War, planes were mainly used as bombers and fighters, sorry. And the rockets were deeply improved by the Germans, especially the V1 and V2, you know. These are V2 rockets. These rockets were designed to bomb the city of London and the South England area. And these rockets were used by the American and by the Russian for the development of their own space program after the war. What are the main significant steps? We can mention Concorde, the famous Concorde supersonic aircraft. The first commercial flight was in 1976. It was a very efficient plane for speedness, but very bad for environment and for the consumption of gas and petrol. So it was now abandoned. And we have also to mention the launch of the first space shuttle in 1981. This was very important. It lasted only 30 years, but the was a very interesting vector because it was possible to reuse the shuttle after the launch. About propulsion, you know probably that physical laws of orbitography were defined a long time ago by scientists such as Kepler, such as Newton in the 17th century, but they were quantified at the end of the 19th century, and particularly by this guy, Tsiolkovsky. Tsiolkovsky was a very efficient mathematician, and for the first time, he quantified, for example, the speed necessary to leave the orbit of the Earth. So he calculated that depending from the area to orbit the satellite, it was necessary to reach a speed of about 8 to 11 kilometers per second to orbit a satellite. And we can also mention Esnault Pelterie, a French guy, Robert Goddard, an American guy, and particularly Wernher von Braun. Von Braun was a promoter of the German space program and weapon program during the Second World War, and he worked for the Nazi government. But after the war, he surrendered to the American, and he worked with them and was especially in charge of the Apollo space program with the well-known success of this program. And von Braun died in 1977. This is a historical view because this is the first image, what we call the first spatial image, because it has been acquired at an altitude of more than 100 kilometers, 104 kilometers exactly over New Mexico. It's relatively difficult to imagine that this is New Mexico, but you can see the land and some clouds and the horizons. But you have to know that as early as 1942, a German rocket reached 90 kilometers of altitude. So it was one key point during the Second World War. You have two physical aspects very important for the war. Is a radar control, and only the British and the Western countries known this techniques. So the German lacked this radar technology, and for the ballistic rockets, this time German were the first, but fortunately we can see that the war ended and it was not possible for the German to improve the rockets because they could destroy a lot of countries, even maybe in North America and Russia, if they succeeded. For propulsion, some steps. The first satellite is a famous Sputnik, you know, with a beep beep, famous beep beep associated to the satellite. It was a very small satellite, only 58 centimeters of diameter and 84 kilograms. And it was launched October 4th in 1957. And the mission ends a few weeks after, and the destruction of the satellite occurred just after 3 months in operation. These are some stamps. This is a Japanese stamp because 1957 was the famous International Geophysical Year. So the contribution of USSR was very great and large, but other programs were developed for geophysics, and particularly geophysics of the Earth. In 1961, the first man in orbit was Yuri Gagarin, this cosmonaut here. And the flight was very, very short because it lasted only 1 hour and 48 minutes. So that means 108 minutes. With the Vostok 1 mission, you have here the track from the start here, start to the east, always to the east, to take benefit of the Earth's rotation, and come back to close to the start point. The start point was and arrival was in northern Russia. The first excursion of a cosmonaut out of the spacecraft was due to Leonov, 1934. Unfortunately, this guy died, I think, last year. And here is a photograph of Leonov in 2015 concerning the 50th anniversary of this first excursion out of the spacecraft. So it was the first time that a guy was out of the spacecraft. During that time, during the year 1960, 1961, we have first satellites only used for global meteorology. This sketch shows a number of launching between 1957 and 1973. And you can see a considerable increase of the launch in the 60s, with a maximum of 140 in 1967. This is the first image acquired by TIROS-1, launched the 1st of April in 1960. That satellite operated only 78 days, but acquired more than 22,000 photographs. So we have different programs with TIROS, TIROS-AIM, and TIROS-N. It was the very first satellite. This is also a seminal picture because this was the first space view of France, here taken by TIROS in 1960. We can recognize the shape of the France coast. Here you have the Baie du Mont-Saint-Michel. Here, these are the British Islands. This is Spain, and this is North Africa. Okay, this is the evolution of the TIROS program, completed by NOAA program. Now we are with number 20. NOAA 1 launched in 1960, but NOAA 20 was launched in 2017. And now what the American calls the Joint Polar Satellite System of the NOAA. And this is a view of France using color composites with NOAA. And this is a very nice picture because it's totally cloud-free. It's rare. It's maybe, in average, we have one data per year or at a maximum. Sometimes you have to wait for some years. So other satellites such as Nimbus 1 or ESA, and note that all satellites described until now were what we call sun-synchronous orbits. I will explain you in another part of the lecture the orbits of the satellite and the link with the acquisition parameters. In the early beginning of industry, it was not possible to put satellites in a geostationary orbit. It is very far from the Earth. It is very difficult to calculate and to decelerate the satellite. The first one was ATS, you know, ATS, Applications Technology Satellite, with a spin scan cloud cover camera. It's an American satellite. It is the first satellite in geostationary orbit, distance of about 36,000 kilometers far from the Earth's surface. And this was the first image showing the Earth and the Moon. You see the Earth and Moon. And here an image of ATS in December 1966, just a few days after the launch. And this was the launch of ATS. Owing to propulsion, it was possible to join the Moon, the famous first step of Neil Armstrong on the Moon, the famous giant leap for mankind, here commemorated by stamps. And this was in 1969. And basically, the propulsion remains the most limiting parameters because photography is well known, and we can reach very detailed camera images. But aeronautics also is well known because we know the design of planes and rockets. But the problem is the propulsion, because it's always the same propulsion using what we call propagol. It is a specific carburant for a kind of kerosene, but adapted to rockets. And right now, one of the best launchers, this is Ariane 5. Here it's the first launch of Ariane 5 in 2005. But you can only have a payload of 20 tons in low orbits, in census orbit, and 10 tons only in geostationary orbit. So it's always a problem in remote sensing. Is it better to design a launcher, a small launcher for launching just one small satellite, such as a Russian launcher, very solid launcher with very few unsucceeded mission. You have maybe 99.5% of good launch, but you can only launch a very small satellite or select a very large launcher such as Ariane 5. So you can launch a few satellites because the satellite's weight is about 1 or 2 tons. So with 10 tons in geostationary orbit, you can launch 3 or 4 satellites, but it's more expensive and it's more dangerous if there is any problem with the launch. And the propulsion leads also to very interesting missions such as Voyager missions or New Horizons into 206, because Voyager visited Jupiter in 1979 or Uranus in January 1986. And here, this is Pluto viewed by New Horizons 9 years after the launch in 250. This is a location of Voyager 1 is here. You see, this is the probe with a large distance from the Earth and the Sun as well. Pioneer 11, Voyager 2, and Pioneer 10. Okay, this was to finish with the propulsion. I think that it's enough right now. I stopped my presentation. I stopped to share the screen. And do you have question? Do you have any question? I know that it's very dense. It's very dense for you, and it's very dense for me as well. So if there is no question, I will send you the presentation of this morning or this afternoon for you. And I will also send you the files on the Mont Saint-Michel Bay. Okay? Maybe I will ask Tra to, because I don't understand the problem with the Zoom link. I think that it will be better if Tra provided me with the link. So I will ask Tra for the next day to have the link by USTH. So, okay, I wish you good evening for you.
Yes, thank you.
See you tomorrow.
Good afternoon for you.